All right, recording started. Good. So this is probably one of the few times we'll have to do this. I intend to try and record the lectures on campus. Gee whiz. Record the lectures on campus anyway, as there'll always be sometimes that some of you can't make it for various factors. So I'm not sure how that's going to work yet. It might just be me with my phone at the front of the class, literally recording and then trying to stick it up onto YouTube later. But that should always be available for people each week. You'll see in the content section there's the link for the for this particular Zoom video. If we ever have to do a Zoom link again in the next 2 months, you should be able to use that exact same link to make that work. And any of the videos will go up on YouTube, and I'll probably create a little folder on Desire to Learn where you can find all those videos as they pile up. Now, I'm not sure what we'll do for lab next week. I really hate to miss a lab. We might do the lab that we were supposed to do yesterday and another laboratory, especially if I can find one which looks like it will be just as quick to get done. Basically, the lab yesterday was just some benzoate, chuck it in some acid, see if it will chemically react, see if we can see any signs that it's chemically reacting, and then write up a paper based on that. That would probably take 50% of our time at most. If I can find another lab that might be quick, then we might try and do that one as well, so we don't fall behind. The big shadow over us is that, of course, maybe at some point in the semester, we'll all be told to stay at home and be completely online. So I wouldn't want to miss an opportunity to, at the very least, stay on track with the number of laboratories, because online virtual laboratories are just never as satisfying for anybody involved. So we'll just keep going as long as we can and take advantage of having lab together as long as we can until such time as things are looking bleak. So we'll try and do 2 labs next week. The one we were supposed to do yesterday would definitely be one of them. And I think maybe not the lab that was actually planned for next week, but one of the ones a couple of weeks down the line. I know there's a couple of labs where you've just got an unknown and you're starting to do just some little tests with different chemicals to try and identify it. We might do one of those labs next week as well, because even if you can't get it finished, there'll be an easy point to stop and then finish it off at some later date. One thing we don't want to try and do is some lab where we mix everything and then reflux it at high temperature for 2 hours, because that's not something you can suddenly stop. So we might do one of the experiments where it's just lots of anecdotal tests trying to identify an unknown. But I'll put up some information by Monday morning at the latest this coming week and let you know what the actual plan is for that lab. But certainly that first acid-base lab is still on the menu for next Wednesday. Anybody have any questions at this point before I start talking? Okay, everybody's all quiet and so polite. Okay, maybe because it's being recorded. Right, so everybody can see my screen. You should have the chapter 1 notes. Incidentally, oh dear, excuse me. Incidentally, you get access to these notes. It's one in the folders for each chapter. You'll always have access to a version of my notes. It's usually about 98% accurate, just with occasional gaps and blanks for doing in some examples. So keep an eye on that. You can follow along with my notes on the page here. Now the first third of the chapter is really just making people aware of some of the scales that they should still retain from classes like 151 or maybe even 152, as some of you might have taken. But keep in mind that for organic chemistry, it's really just about down to just carbon and hydrogen for the molecules what we will be looking at. We sometimes get a bit excited if we can add in a bit of nitrogen or a little bit of oxygen for an alcohol or an ether, and the halogens often make an appearance as well. But that's just about it. Other than some organometallic chemistry, we won't be talking about metals, which of course is a vast majority of the periodic table, and we very rarely mention any metalloids either, like boron or antimony and things. So there's very few elements that we're looking at, but we can combine those elements in such a crazy number of different ways. It gives us a huge variety of compounds. So things to be aware of, which I'm sure you are. I've become addicted to orange and peach flavouring of late for some reason. Things you should be aware of course, just the basic build-up of an atom with protons, electrons and neutrons. The protons and neutrons are in the centre of the atom, giving us the mass to the atom. And the electrons are outside the nucleus, negatively charged, almost weightless, but not quite. But certainly in terms of a comparison to protons and neutrons, we consider them to be virtually weightless. Because we've got an atomic number for atoms of each element, which is the number of protons, that's unique. We get a mass number for the atoms of each element, and that mass can change because we have isotopes with different numbers of neutrons. That's what we call isotopes. Of course, when it comes to the electrons, those electrons are found, according to Bohr, are found in quantized energy levels. And it's a little bit like layers of an apartment building. You're either on the first floor or the second floor, and you're not somewhere in between, stuck between floors, or you're on the second floor or the third floor, etc. That's kind of how we find electrons. There's areas around the nucleus where we find a dense area of electron density, and then there's a gap where we find pretty much nothing, and then a band or area, a shell of electrons again, then a gap. And so with a little bit of tweaking, it's more or less finding electrons in shells, layers of electrons, occupying these orbital spaces. An orbital is just a fancy way of saying the simplest space that we can describe, where we can find up to a maximum of 2 electrons, and with a probability of 95% or greater, those 2 electrons are somewhere within this space. We get different kinds of orbitals or different kinds of subshells. Excuse me. We talk about the s orbital, which is just a sphere around the nucleus. So somewhere in that space, because I can use my pen for this as well. So somewhere within this space, but without going into the nucleus, we find the electrons, because they're moving around with kinetic energy. Just like if they looked at a time-lapse video of your house, although why they'd be spying on your house, I'm not sure. That's probably against the law. Over time, over the course of an evening, maybe you'd be in the kitchen for some time, maybe you'd be in the living room or in the laundry room for some part, just on the move and somewhere within that limit. And that's all we mean by an orbital. We're defining a space where there's a very high probability to finding those 1 or 2 electrons each time. So that s orbital, it has a spherical shape. The p orbital is like a propeller blade either side of the nucleus, and they build up. So there's the first one up and down on the x or the y-axis, and then there's a second one which will draw very badly along the y-axis, And then going into the page and out of the page towards us is that final orbital. So they make up the points of an iron cross in 3 directions, in our 3 dimensions. And we're just saying that there's up to a maximum of 2 electrons in each of those individual orbitals. So a p subshell can take a maximum of 6. And of course we have a variety of d subshells, 5 in all, 2 electrons per orbital. So we get a total of 10 electrons in a d subshell. I'm sure that wasn't anything startlingly new for anybody, but these are the kinds of little things to make sure that we're still on board with, and we haven't completely had our minds erased over the extended summer. So they arrange themselves into layers, these shells, and the further out we go from the nucleus, the more kinds of subshells we see. So in the first shell, there's only an s subshell, which can take 2 electrons. Move up into the second shell, we see the s and the p to give us a total of 8. And then in the third shell, we eventually see a d subshell as well, which takes a total up to 18. That's usually about as far as we take it. If you go further, we see the f subshell, which can take 14, etc. From some of your earlier chemistry, you're probably used to having the subshells and orbitals represented by individual boxes, each box representing 1 individual orbital, which can take a maximum of 2 electrons. Another thing you've probably seen is that when you're representing these electrons into these little block diagrams, oh, is my pen not working? So we take a box representing an orbital. We draw the electrons as a half-headed arrow, and it's trying to represent the direction of spin for that electron. It's moving around, of course, within the orbital, but as it moves, it's got a direction of internal spin. So when you take a second electron and align it up with the first inside that same orbital, you'll always point the other arrow in the opposite direction. The electrons are negatively charged, and when you put them this close to each other, and although still spinning, they naturally spin in opposite directions to alleviate some of that friction. And I'd be surprised if that was new to you. It's very important to just give people a gradual start for this stuff. Okay, so when we try and use atomic theory and build up the electrons into the shells, we use 3 ideas. We have got Aufbau principle, or build-up principle, that tells us that we fill the orbitals and subshells of lowest energy, the ones closest to the nucleus, and build up, almost as if people in an apartment building were trying to get an apartment room as close to the ground floor as possible. We've got Pauli exclusion principle that tells us that any one orbital can only have a maximum of 2 electrons. And then Hund's rule, which tells us about the d and p subshells, which are made up of multiple orbitals. So I've got go back to my pencil here. I've got a 3p subshell here, and then a 3d. Idea being that, like an apartment which has multiple bedrooms, the first person moves in here. When the second person moves in, when the second electron comes along, why would he share? He could get his own separate bedroom next door, the same as the third one. It's only when the subshell is half filled, now the electrons will start to pair up, because this involves less energy than moving up to the next energy level. It's like if the electrons were people, you're saying that the electrons are antisocial. They don't want to share if they don't have to, but they're also lazy. They want to stay as close to the nucleus as possible, as close to the ground state as possible. And so they're more lazy than antisocial. And so when those orbitals become half filled for the current subshell, I didn't mean to do that. There we go. When it's half full, it's easier to share than going to all the expensive energy to move up to the next subshell. Again, just a very broad 151 idea. Nothing startling there. One thing that I do find sometimes that people are not aware of is that you don't have to memorize the order that the subshells appear. You can just use the periodic table for that. And let me pull up a periodic table to show you what I mean. Basically, each row, each period, is normally like a particular shell. Each box, as you go across the period, is like electrons going into the shell. And the particular block of the table, like the left-hand block, the middle transition block, and the right-hand P block, are like electrons going into those particular kinds of subshell. So let's see if I can pull up a periodic table. There we go. There we go. So if we look at the configuration for something like, let me change colors as well, make it a bit more exciting. Let's say we're looking at the configuration of something like manganese, right in the middle of the table there. Because the configuration, as we normally write it for manganese, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, just about got room here, 1, 2, 3, 4, 5, and then 3d5. I'll just squeeze that in there. That configuration is based on the shape of the table, because when Dmitry Mendeleev created the periodic table, it was based on the relative chemical reactivity of the elements. And that reactivity is based on where we find the electrons in the shells, specifically the outer shell, that valence shell. So we do have to use a bit of artistic merit here. So we pretend that helium is right next door to hydrogen on the left-hand side of the table. It's a bit of a cheat there. So we ignore it being there. As we count boxes, we're counting electrons. And so we're in the first period. So we're in the first shell. Is that me beeping? Can anybody hear a kind of beeping every 30 seconds? I wonder if it's something I'm doing. Maybe. Oh, you know what it is? I bet my headset is getting close to running out of power. So let me plug it in and get it charging. I'm not sure if somebody has some kind of beeping thing to try and get my attention or something. Hang on. Okay. Let's see. All right, just getting paranoid, mate. Want to make sure I was recording. So let's see. So the 1 is for the first period because we're talking about the first shell. And we count hydrogen and helium. We're on the left-hand side, so that's electrons going into an S subshell. 2 boxes, so an electron count of 2. Then we have to jump down into the second period. So we're into the second shell. Back on the left, so it's the S subshell once more, counting lithium and beryllium. So 2 electrons. We then jump across to the right-hand side for the first time proper, but still in the second period, so it's still the second shell. And when we count boxes on this right-hand block, We're imagining them going into a P subshell, and we can count boron through neon, 1, 2, 3, 4, 5, 6 boxes. So 6 electrons for the configuration. Drop down into the third row. So we're into the third shell. Back on the left with the S block, sodium magnesium, so we get 3s2. Then aluminium, or aluminum for our American friends, aluminum through to argon, 6 boxes to give us 3p6. Then into the fourth period, so potassium and calcium, giving us 4s2. Then finally, with this middle block, which represents the D subshell, we count 1, 2, 3, 4, 5 boxes for 3d5. D subshell is always one behind the period count on the table. You've probably heard about this from your 151 classes. We say that the S subshell is more penetrating. And so when we should be putting electrons into the D, the first 2 electrons each time can actually slip into the next S subshell before we go back and then put electrons into the D subshell. So D is always bleeding slightly out of order, always comes behind the next S subshell. That you are probably aware of, but I do sometimes catch people joining 201 and have never seen this idea of just using the periodic table to work out the electron configuration. Was that new to anybody? Did I shock anybody?
That was actually pretty new to me. So.
Okay. So it wasn't just some old guy inanely talking away about something. So that is something I do find on a regular basis. That, oh, I'm sorry. Everybody hear me okay? I'm such a klutz. I didn't have my second.
Yeah, mate, I was just using the old computer speaker. So I probably now sound a bit better, yes? Would that be fair to say? Yeah, okay. It might have been a little bit echoey with for the first 20 minutes. I am so sorry. I keep forgetting things like that. Anyway, okay. So I often find that's useful to point out. Just use the shape of the periodic table and you'll never go wrong. Same thing when you get to the lanthanide and actinide series when they eventually come in. Of course, they are 2 behind the number. So first time we see the middle block here, that's the 3D. So this would be the 4D, this would be the 5D. Likewise, when we see the for cerium and the others, they are 2 behind the position that they are in. And that's just a natural staggering of the subshells and the order they appear. So a periodic table is all you need for an electron configuration. And in an exam, I would always give you an electron configuration. Well, I'd always give you a periodic table. I don't expect anybody to have the periodic table memorized. I can probably go up to about maybe 80 from memory, but I can't remember them all, especially some of the weird names we get down here at the bottom. Okay. Let me clear that. Let's see what other things we should be thinking about. I think it's Lewis structures next. So we should have had a lot of practice with the electron configurations. Sometimes we write the shorthand configuration because the most important information is about that last layer. Because when the chemical reactions happen, boom, it's the electrons in the front line, the electrons in the outer shell, which come into contact with that collision and get exchanged. Once a shell has been completed, it's very rare for them to ever be disturbed again, other than some kind of photometric excitation or something. So the really important thing for magnesium is that it's 3s2, 2 electrons in its outer valence shell. And so those first 2 shells complete can be summarized as neon. And so sometimes you'll see neon written in square parentheses. For something like, say, what else could we do? something like iron. Just going to improvise this one here. Oop. Get my pen working again. So we're trying to write the configuration for iron. At the end of the third row, of course, we've got argon. I think it's argon at the end of the third row. So we use the chemical symbol to summarize those three layers. And then we just write it as 4s2, 3d6 for the rest of its configuration. Is that a question for me? Or just talking to somebody in the room? That sometimes happens, of course. I do apologize ahead of time. Occasionally, you might see my kids stampeding in here trying to talk to me. Okay, so I don't think there's anything shocking in this first half hour. Let's see. You're probably used to, of course, drawing Lewis structures from 151. I have a particular method for it, which I just want to quickly talk about now. When you look at the chemical formula, and the example to use is hydrogen cyanide here, HCN. First thing is just use the periodic table to get a valence electron count. How many boxes do we count to reach that element in the particular period that it's in? So hydrogen's the first element in the first row. Carbon's the fourth element in the fourth row, so it has 4 valence electrons. Nitrogen's the fifth element in the second period, so it has 5 valence electrons. That gives us a total of 10. And we can build a Lewis structure using just those 10 electrons. Having chosen having counted the valence electrons, we then choose with small molecules which element would be the central atom. Now, you probably had it taught to you in 151 to choose the one with the lowest electronegativity value that's not hydrogen, and that's fine, but of course that assumes that you've got an electronegativity table to hand. If you didn't have it, the most commonly found choice would be which of those elements needs the most electrons to complete its shell. Carbon has 4, but it needs another 4 to make an octet, so its combining power is 4. We expect 4 chemical bonds. One nitrogen has 5, needs just another 3 to make an octet, so it needs only 3 electrons and would normally be expected to make 3 chemical bonds. And of course, hydrogen needs just 1 more to look like helium, so it's only normally expected to make 1 chemical bond. So something like hydrogen cyanide, you would choose carbon for the central atom because it needs to make the most bonds. And that's a good general guideline if you don't have a table of electronegativities at hand. Now, if you have a tie with the chemical formula that you're looking at, so if, for example, you had a chemical formula that contained both oxygen and sulfur, they're above and below each other in group 6 of the periodic table. So who do you choose then? Again, if we had the electronegativities, that would make it easier. But without that electronegativity table, choose the element which is lower in the table because it's the bigger element. And that would probably be the correct choice for the central atom. So try and find the element which needs to make the most bonds. But if there are certain elements which are tied for this, go with the one which is bigger further down in the table. And using that logic, that usually takes you to each time the element with the lowest electronegativities. Just something to bear in mind if you don't have an electronegativities table handy. So choosing carbon for this one, we put carbon at the center and we immediately draw a line representing a chemical bond to the other atoms in the formula. This is, of course, assuming that we've only got one atom at the center, a relatively simple molecule. Each line is a bonding pair of electrons, so 2 and 2, 4. We've only got 6 electrons left as we try and build the structure. But that gives us the basic skeleton for the molecule most of the time. And then with those remaining 6 electrons, we use them to try and fill the shells with duets and octets. Because the hydrogen only needing 2 electrons to look like helium, that one bond already fills the duet for hydrogen. You never draw lone pairs on a hydrogen. It doesn't have an octet, it's just a duet. Never draw lone pairs on a hydrogen. That makes Dr. Elliott mad. Mad, I say. So we can use those 6 electrons to complete the shell of the nitrogen together with the chemical bond. So it has an octet. But we've run out of electrons before we can complete the octet of the carbon. Just 2 bonds, 4 electrons. So as a last step, if you do run out of electrons, turn the lone pairs into bonding pairs to complete the octet of the neighboring atom. So to come to the rescue of the carbon, that carbon could use 2 and 2, another 4 electrons, and with the triple bond in place, the carbon now sees an octet. That's probably one of the most important skills coming into 201 from 151, just understanding the need for octets to be complete when you draw molecules in organic chemistry. Excuse me. So for example, if we try this idea on a molecule, let's see, these are some of the examples here. Now, again, it's just a suggestion. I don't always go through them with everybody because this is just revision. There's nothing really startlingly new at this point. That changes quickly enough, of course. If we quickly do, let's see, let's do the carbonate. So we take the carbonate formula, CO3, 2 minus. For carbon, it has 4 electrons in its valence shell. That's what the periodic table tells us. It's 6 for each oxygen because it's the 6th element in the second period. And then we've got that electrical charge as well, which is telling us that we've got 2 more than we'd normally expect. Species which are negatively charged have a surplus of electrons. So the total electron count for this polyatomic ion is 24. Between carbon and oxygen, carbon atoms need more electrons to complete their shell, so we'll stick it to the center. If we had a table of electronegativities, we could have just cheated and seen that carbon has the lowest electronegativity for a non-hydrogen element. We connect it to its neighbors, so 2, 4, 6 electrons. That takes us down to 18. We'll use the remaining electrons to fill octets, but we start on the outside and work our way in if we have any left. 6 electrons to each oxygen for an octet, but that uses up our supply. And the carbon in the middle still doesn't have an octet, 2, 4, 6. So as we talked about with the hydrogen cyanide example, we borrow a lone pair and reimagine them as a bonding pair. Now we have the octets. Of course, we'll talk about this in chapter 2 next week, but do remember as well that we have formal charge, -2 in the molecule, and we can see that in the individual atoms by using the periodic table count compared to the Lewis structure count. By the periodic table, I mean just literally the position of that element in the periodic table, as we've been doing. So for carbon, let's see. Come on. Where'd my periodic table go? There we go. Carbon there, so 1, 2, 3, 4 electrons for carbon, 1, 2, 3, 4, 5, 6 for oxygen. So the table tells us, oh no, I erased my picture. What a klutz I am. I can cheat and quickly put it back in where we were. So we had that there. As you have probably no doubt suspecting, I'm not the greatest artist in the world. So that periodic table count compared to what we see in the Lewis structure, carbon should control 4. And as we count the electrons, remember these are bonding pairs, so they are shared between the two atoms. So just 1, 2, 3, 4 electrons belonging to the carbon. So it's actually electrically neutral in our structure. Same with the double bonded oxygen. So double bonded oxygen should control 6, and it does control 6. 1, 2, 3, 4, and then 1 from each bond, 5, 6. So electrically neutral as well. And that's always going to be true for oxygen if it has 2 bonds and 2 lone pairs. That makes it neutral. But the single bonded oxygens should control 6, but actually control 1, 2, 3, 4, 5, 6, and 1 of the 2 electrons in the line, in the bond. So actually control 7, and has a formal charge of -1. And so formal charge of -1 there, formal charge of -1 there, and they combine to give us the charge of the polyatomic ion, 2-. Those individual atom formal charges always give us the sum of the parts. Again, nothing particularly new there, I would wager. Right, excellent. That is a good point to take a break before we do another half hour or so, because now we're starting to edge towards either new ideas or at least ideas you might be a bit more rusty about, like hybridization. Okay. Any questions before we take a break? So polite, so quiet today. So let's take a break for 10 minutes. We'll come back at, I guess that's going to be 2:50. And that'll give us a last 25 minutes. And we should get close to the end of the first chapter, which should be a good start because it is mostly just revision. Okay, back in 10, guys. And if I don't say anything, okay, we're back. Let's look at some ideas in bonding. Now, you're probably familiar with valence bonding theory. It's straightforward from atomic orbital theory. These orbitals overlapping in that space, that mutual space between the two nuclei to create a chemical bond. And so the electron density in the chemical bond is focused in that plane between the two nuclei. And that's what we call a sigma bond. When it's a direct route between the two atoms, between the nuclei, that's where we find the electrons. And that's where the attraction, of course, would be strongest. Those negatively charged electrons attracted to the positively charged protons in each nucleus. And that gives the strength of the sigma bond. You can see for hydrogen, excuse me, I took an extra dose of my blood pressure medication last night, and it's one of the side effects, and it just makes me cough a little bit annoyingly. When we look at that hydrogen bond, it takes 456 kilojoules per mole of energy to make the bond, and if we were to try and break the bond, it would need that amount of energy put back in. Conservation of energy, the energy that goes in to break the bond is equal to the energy released when the bonds originally form. And so for any chemical bond, there's always an optimum minimum energy for that bond. As we see here at the bottom in our valley, the energy starts to rise as the atoms get too close together. That's when positively charged protons become aware and repelled by positively charged protons in the other nucleus. If the atoms drift too far apart, the energy starts to rise again. because those electrons are losing their attraction to the positively charged protons in each nucleus. Now, valence bond theory, these sigma bonds, is a nice idea as far as it goes, but it can't explain everything for us. And a classic example of that is with something like methane. We've got CH4 for methane, the carbon at the center, and it takes up this tetrahedral stance, of course, around the carbon with those 4 chemical bonds spacing themselves out as far away as they can from each other bond. That's our VESPA theory, valence shell electron pair repulsion theory. And it creates a bond angle of 109.4 degrees on average. Trouble is, for the carbon atom, we're using s atomic orbitals and p atomic orbitals. As we saw earlier, the s atomic orbital was shaped like a sphere, but the p was shaped like a propeller blade. If we're using different kinds of orbitals with different kinds of shapes, there's no way we could get this kind of symmetry around the carbon atom using different kinds of orbitals to make these bonds. So atomic theory is too simple to explain what's going on with this high degree of symmetry in a molecule of methane. So this is when we move to hybridization theory again. As you no doubt probably remember from 151, we're treating the orbitals like wave functions. Basically, it was said that a wave can exhibit the properties of a particle, and it was therefore surmised that a particle in motion could act like a wave. And so we use these ideas to create these mathematical equations, which we call wave equations. And we treat these wave equations as coming together either constructively or destructively, coming together in phase or out of phase. And depending on how they come together and the kinds of orbitals used, we create different levels of hybridization. So for example, if we take the s orbital in the second shell of a carbon atom with the 3 p orbitals from the p subshell, if we imagine them coming together as wave functions, together they would produce these 4 hybrid orbitals. Now the plus and minuses are not meant to represent charge, they're just meant to represent whether that part of the wave function is coming together in phase or out of phase with each other. And so the pink side are coming together in phase constructively, and so that produces an orbital which is larger than normal on that side, but the blue coming together with the pink on the other side of the p atomic orbital, they're coming together destructively or out of phase, and just like 2 water waves which come together out of phase, they would cancel each other out to some degree. And so the other side of the new hybrid orbitals which are produced has shrunk in size. And so we produce these new hybrid orbitals. We used 1s atomic orbital and 3 p atomic orbitals, 4 in total. And for each atomic orbital used, you produce a hybrid orbital. And so we've got 4 of these sp3 hybrid orbitals. The sp3 telling us which atomic orbitals were used to make them. So each one of these 4 is described as an sp3 hybrid orbital. Now that we've got 4 orbitals of the same shape and energy, it's much easier to imagine these hybrid orbitals coming together and spacing out to give that tetrahedral shape. That is difficult to explain using atomic orbitals of different shapes. But now we've got 4 equal, identical, hybrid sp3 orbitals. And just as you would expect from hybrid orbital theory, they space out around the carbon nucleus as far away from each other as possible. And so we get this tetrahedral shape with these 4 equal sp3 hybridized orbitals. Nitrogen is similar, although one of the orbitals is going to have a lone pair of electrons. And so we normally only see 3 chemical bonds for the nitrogen. So of course, although it's still sp3 hybridization, that lone pair means that there isn't a physical chemical connection to that part of the molecule. And the shape of these nitrogen-based molecules would look to be trigonal pyramidal, which in Britain is sometimes referred to as truncated tetrahedral. Just write that out. So we've got 1, 2, 3 chemical bonds, and then just a lone pair which isn't attached to anything. And it creates this trigonal pyramidal shape. 3 bonds and 1 lone pair. That's the name you're probably used to from 151. But in the wonderful Great Britain, where I come from, this is what we'd sometimes call truncated tetrahedral. Oops, if I could spell it. Just about fit it in. So this is just a heads up. If you hear me talk about truncated tetrahedral during the semester, slipping back to my British roots, I'm just talking about trigonal pyramidal. Okay. Okay. So if we use all 4 atomic orbitals, we produce 4 sp3 hybridized orbitals. And they space themselves out as far as possible and normally produce a tetrahedral shape with a bond angle of 109.4. Switch a bonding pair for a lone pair and it becomes a trigonal pyramidal. Sometimes the s orbital and just 2 of the p orbitals come together in hybridization. And so we now produce 3 of these sp2 hybridized orbitals. We're using 3 of the atomic orbitals, so we produce 3 hybrid orbitals, and each of them are called sp2 hybrid orbitals because that's the atomic orbitals that were used to make these new hybrid orbitals. So these 3 hybrid orbitals in pink. Remember, as we'd said before, the shape should really be, I use my pen again, the true shape is going to be with the nucleus in the center. One side is where everything has come together in phase constructively, and then there's a little bit round the back which is destructively out of phase. As you'll see with these pictures here, I tend to just ignore that part because most of the bonding is on that much more swollen, larger lobe side, and it's just easier to draw if I leave out that little fiddly bit round the back of each of these orbitals. Okay, so those 3 sp2 hybridized orbitals space themselves out in this trigonal planar arrangement around the central atom, which is most of the time going to be a carbon. So this is synonymous with sp2 hybridization, this trigonal planar shape. Does what it says on the box. They're making up the points of a triangle, and they're all flat in the same plane. Of course, then with that unhybridized atomic orbital still there above and below the plane. We don't consider the atomic orbitals that are left when we space out the hybrid orbitals. Those hybrid orbitals are focused on getting as far away from each other as possible. And with only 3, they can comfortably split up into this trigonal planar arrangement, giving us a bond angle of 120 degrees each time between them. goes from the hybrid orbital to the atomic orbital. That's an angle of just 90 degrees. So any atom which is sp2 hybridized usually has a trigonal planar shape associated with it. Finally, sometimes we see the s atomic orbital and just one of the p atomic orbitals come together to give us sp hybridization. By the way, in terms of carbon, with 3 hybrid orbitals and 1 atomic orbital, that atomic orbital is normally used for a pi bond between itself and a neighboring carbon atom. So there's electron density overlap here and here for those 2 atomic orbitals. It's hard to draw it without it looking cluttered. And with the electron density outside of that plane for the 2 carbon nuclei, this is called a pi bond. And of course, the hybrid orbital is being used for the bond directly between the 2 carbon atoms, which we talked about in valence bond theory. That's still what we would call a sigma bond. So the first bond that forms between any 2 atoms always takes that direct route. And that's probably going to be using the hybrid orbitals, and that's what we'll call the sigma bond. If a second bond comes into play, it's got to reach around this bond. We can't put all 4 electrons in the same space. So if it has to reach around where the original bond is, that's then using these atomic orbitals above and below the plane, or at least perpendicular to the plane of the hybrid orbitals. And these are what we call pi bonds when they're reaching around a sigma bond. So then finally, sp hybridization, as the name suggests, using just an s atomic orbital and 1 of the p atomic orbitals, we produce 2 of these sp hybrid orbitals. Again, the focus is on them getting as far away from each other as possible. And so we see them pointing on opposite sides of the carbon. And that gives us 2 atomic orbitals which were not part of the hybridization. Use a different color. One of them, as we saw in sp2, one of the atomic p orbitals, which is above and below the plane, and then a second atomic orbital, trying to get away from the hybrid orbitals, but also get away from the other atomic orbital, sticks out in the other last dimension on the z-axis. So atomic orbitals and the hybrid orbitals always have an angle of 90 degrees to each other each time. Focus principally on the hybrid orbitals here, and because of that stretching across either side of the nucleus, that gives us a bond angle principally at 180 degrees, and any molecules using or any atoms I should say, using sp hybridization will be linear at that point in the molecule. First atomic orbital used for a 1 pi bond, second atomic orbital used for a 2nd pi bond. So we're principally talking about atoms which either have 2 double bonds to 2 separate atoms or are part of a triple bond to another atom. I do have a little video like the acid base one I put up the other day called Organic Talk or Organic Chem Talk. And I'll put that hybridization video up soon. So again, trying to mimic a carbon-to-carbon triple bond. So the first bond is overlapping here and here with that pair of orbitals. I always show them distinctly separate just to make it a more clear picture. And then there's a second pi bond between the 2 orbitals there, and then on the other side there. And so we get that carbon to carbon triple bond. Reality is, all you really have to remember is these 3 levels of hybridization. So it's kind of easy compared to what you got in 151. You would have no doubt talked about much more complex structures, but that was with elements which had access to atomic orbitals in the d subshell. Carbon does not. Carbon does not have any electrons in its d subshell. That's too high. It's completely empty. So the only hybridizations we have to do in 201 and 202 are sp3, which generally take a tetrahedral shape, and that's usually for carbons with just single bonds, or sp2, which normally takes a trigonal planar shape, and that's carbons which are involved in a double bond like ethene. And then sp hybridization for atoms like for atoms which are part of a carbon to carbon triple bond normally, or it could be that they're double bonded to 2 separate elements, and they normally take a linear shape because the 2 hybrid orbitals produced are on exactly opposite sides of the carbon nucleus. And so we can use these ideas to work out the hybridization for any atoms in our structure. So this is where we'll finish today. I think, how much have we got left actually? Not that I'm looking to talk for any longer, but so molecular orbital theory, which we'll just touch on, line algo formulas. Okay, not too much more to do for chapter 1. So we've just maybe just nudged people into a little bit of a rusty, dusty brain cells which haven't thought about this stuff for a while. Let's see. So looking at this carbon here, count the number of sigma bonds. You're counting the number of atomic orbitals used to make that level of hybridization. So 1, 2, 3, 4 bonds around it. That would need 4 atomic orbitals, s, and all 3 of the p. So it's sp3 hybridization. The oxygen next to it, counting 1, 2, and then the lone pairs, we'll add them in as well. So 4 pairs of electrons, so that would again be sp3. Same with the carbon here, counting the bonds around it, 1, 2, 3, 4. So needing 4 atomic orbitals, the s and all 3 of the p. So that would give us 4 sp3 hybrid orbitals. Each of the hybrid orbitals is referred to as sp3 because it alludes to the atomic orbitals that were used to actually make it. And then along here with the nitrogen, 1, 2, 3, and then that lone pair 4. So sp3 again. And the carbon next door. Again, we're just counting lone pairs and sigma bonds. So we count that, we count that, we count that bond, but we don't count that last bond because that's a pi bond between the carbon atoms. We don't count pi bonds towards hybridization because those bonds are using atomic orbitals that were not used for hybridization. So 1, 2, 3 sigma bonds. So 3 atomic orbitals, s, p, 2. The 2 p's and the 1 s, so 3 atomic orbitals. And the same with its neighbor, which also has that carbon-to-carbon double bond around it. So 1, 2, 3 bonds used. So 3 atomic orbitals created that hybridization level. Basically, if it's a carbon with just single bonds, it's sp3. If it's a carbon with a double bond, whatever else is attached, that would be sp2. And if it's a carbon in a triple bond, or a carbon which is double bonded on one side and double bonded on the other, like say carbon and carbon dioxide, CO2, they are both examples of sp hybridization. I've got one sigma bond there, one sigma bond there, one sigma bond there. And of course, there's something else attached to the carbons each time, which should also be a sigma bond. So just 2 sigma bonds and 2 being pi. So just 2 atomic orbitals used. Any questions before we stampede for the exits? We're doing okay? Hopefully not too much that was startlingly new for people. I'm sure from 151, you've done hybridization with Mr. Mackenzie before, if you took it at Logan. I'm sure he did it very well. Any questions? Silence. Somewhere in the distance, a dog barked. Okay, too shy, everyone's too shy. There's no silly questions, and nobody ever asks too many questions. I don't believe in that. That's just a nonsense. I'm not doing my job if I don't answer questions. Okay. Even just something like sometimes people feel brave enough to say, could you maybe repeat that? Or could we look at another example? That maybe is kind of a code I sometimes get. But always be ready to interject and stop me. You could shout something, whether we're in class, you could shout something respectful like, stop foreigner, and we can take things a little bit more slowly. It can be very intense, but we're going to walk through everything assuming that you have no knowledge of that particular idea or theory. Okay. One of the nice things is we get to keep the math to an absolute minimum. There's almost zero math in the class this semester. Okay. Right, I'll pause or stop.